I would invite the speaker Lee Soon, she will present us a computerly efficient finite element approach for residual stress induced by additive manufacturing. Please.
Thanks for Chairman. Thank everyone for coming. I'm Li Sun from Norwegian University of Science and Technology. Today I'm delighted to be here to give a talk, and it is about a new method to estimate the residual stress in additive manufacturing, characterized by point heat source. And my talk is divided into 4 parts. I will start with the background, then I will introduce the point heat source model. Next is the 3-segment residual stress model. And the last part is conclusion. As we all know, for additive manufacturing, the components are built up in layers by depositing material. So during the process, the temperature changes rapidly. During the thermal cycle process, the non-uniform extraction and contraction and expansion will bring residual stress and distortion. And more specifically, the residual stress originates from differential plastic flow, non-uniform temperature distribution, and phase transformation. And residual stress can bring distortion, fatigue, and reduce fatigue life, corrosion resistance, and fracture strength. So for additive manufacturing, residual stress is a big challenge, and to predicting residual stress is more important. And many research work has been done to predict residual stress, and the finite element method was widely used. But for large components, finite element model always be very complex, and it will take a lot of computational time. So now to understand the thermomechanical performance in additive manufacturing deeply and develop a more efficient method to estimate the residual stress, the point heat source model was proposed. So the top left figure shows the physical model. It is the point heat source in the middle of the semi-infinite body, and the process includes heating and cooling process. This is my axis metric model. Here is the heat source, and the radius of it is about 5 millimeter. And the size of the model is 10 times the radius of the heat source. Then I will analyze the temperature history and the stress history, then try to propose a new method to estimate the residual stress. In my work, the material is aluminum alloy 2319, and all of these parameters depend on temperature, the conductivity, coefficient of thermal expansion, specific heat, Young's modulus, and the yield strength and the stress strain curve. Before showing simulation results, I would like to analyze the key parameters affecting residual strain first. Residual plastic strain is also named inherent strain, and it is considered with the source causing residual strain and distortion. So, for one node, the residual plastic strain is equal to the plastic strain plus thermal strain, and the plastic strain is depends on Tm. Tm is the maximum temperature of the whole model, and the location of the node, like this, and the theta is the angle to the heat surface, and the d is the distance from this point to the center point. So theta and d can show the position of the node. And the thermal strain depends on Tp. Tp is the peak temperature of the node experienced. So based on analysis, we know that the residual stress is related to the position of the node and the maximum temperature of the model and the peak temperature the node ever experienced during the process. So in the following slides, I will show you how to get this function. First, the residual stress and the peak temperature are extracted of each node along different directions, and these three figures show three directions, and the different colors show different heat flux. From these figures, we can know that in one direction, all of these curves are very close. And another important is we can find two critical temperature. First, this is the first critical temperature. It divides the model into a yield zone and a transition zone. It means if the peak temperature of the node is higher than this temperature, then the material is yield. If the temperature is lower than this temperature, it is the transition zone. And the second critical temperature is here. The residual stress of this point is about 20 megapascal. So based on this two critical temperatures, the model can be divided yield zone, transition zone, and edge zone. So the three segment model was proposed. It means if we know T1 and T2 and the peak temperature distribution, then we can know the residual stress distribution. So now my target is try to get this function. Residual stress is a function of T1, T2, and Tp. Then I will introduce how to calculate T1, T2, Tp separately. First is T1. From the simulation results, we know that no matter how much the angle is, T1 is almost constant. It's about 330 degrees. It is also can be calculated by this function. But for T2 is related to the angle. The angle is the angle to the heat surface. So another function is a quadratic function. Another problem is how to calculate the Tp. Peak temperature distribution are shown in these three figures, and different colors show different heat flux. We can know that in the same direction, the curves are similar in shape. So all of these data are normalized by dividing the maximum temperature of the model. So for these three figures, the y-axis is Tp divided Tm. Then I plot all of these curves in one figure. From this figure, we can know that for this part, there are big differences among these curves, but it is not important because for this part it is the yield zone. It means no matter how much the temperature is, the residual stress equal to yield stress. But for this part it is important. From these curves we can know that all of these curves are very close. So I just use one curve to fit all of this data. Then I got this function. So based on this function, I can calculate the Tp, the peak temperature of the node experienced by the Tm, the maximum temperature of the whole model, and the distance to the center point. So the the distance can be measured, but how to calculate TP is another problem. Then we found that the maximum of the whole model is linear to the heat flux, and we got this function. So now we can calculate Tm based on Q. Q is the basic parameter. And calculate Tp by Tm and the distance. So now let me give you a summary of three-segment residual stress model. First, based on analysis, we know that residual stress is related to the position of the node and the maximum temperature of the node experienced and the maximum temperature of the whole model. But we don't know what its function is. Now, the three-segment model was proposed. So based on this model, we know that we can calculate the residual stress by T1, T2, and the peak temperature. And T1 is constant, it is equal to 330 degrees. And T2 is a function of the angle. Then we know that residual stress is a function of the angle and the distance and the peak temperature. And peak temperature is a function of Tm, the maximum temperature of the model, and the distance. So, and we can calculate Tm by the heat flux. So, we got the final function. Residual stress is a function of the heat flux and the angle to the heat surface and the distance to the center point. So it means if we know the position of the node and we know how much the heat flux input, then we can calculate the residual stress distribution. And the three-segment model was validated by finite element simulation results in three directions. And the black curve shows the finite element model results, and the red curve shows the three-segment model results. And from these figures, we know that the three-segment model shows good agreement with the finite element simulation results. And we also, and the three-segment model was validated by finite element model in additive manufacturing. So this is the finite element model simulating the additive manufacturing process with moving heat cells and adding material model. And the black curve show the simulation result from this model, and the red curve show my model, the three-segment model results. And from this figure, we can know that the three-segment model can capture the two critical points precisely and show good agreement with the simulation results of additive manufacturing model. But the applicable condition should be mentioned. The three-dimensional size of the substrate should be much larger than the size of the heat source. So let me give you the main conclusion. The three-segment model was proposed to calculate residual stress, and the results of it give a good agreement with the finite element results. And the new method works more efficiently for estimating residual stress and displaying great potential for additive manufacturing. Thank you for your attention.